propulsion. Go. EDL phase lead. Go.
We have deemed Perseverance ready to execute entry, descent, and landing on her own.
Confirmation of entry interface. Perseverance is currently going 5.3 kilometers per second, about 120 kilometers from the surface of Mars. It will start controlling its path to the landing target. Parachute has deployed and we are seeing significant deceleration. The heat shield has been separated. Perseverance now has radar lock on the ground. The back shell has separated. Skyfin maneuver has started, about 20 meters off the surface.
Tango Delta, nominal.
Touchdown confirmed. Perseverance safely on the surface of Mars, ready to begin seeking the sands of past life.
To really bring this to life and show us how this site came to be. So here we are 3.8 billion years ago, and we're about to see the impactor that is going to create Jezero Crater. So here it is speeding towards the surface, and boom, we have Jezero Crater formed. Quite a catastrophic event, perhaps at a time when we had water on the surface. So here we have Jezero Crater. It is now here in this landscape. And what we see now is we know, based on what we see from orbit and now on the ground, that water rushed into this crater from at least a couple channels on the crater walls. And here we see it filling up. And we have conclusive evidence that this crater did indeed fill up all the way to the brim. And we know that it actually overflowed. And there aren't that many craters on Mars where we can say that. And so we know that there was water in this crater for geologically significant amounts of time. And here we see that outflow channel. And as we zoom in here, we're going to see over time, of course, that lake dried up. It disappeared. And eventually it leaves us with the fossil landscape that we have to explore with the Perseverance rover today.
I just love that animation. That's so cool. The main question we're getting a lot right now through our chats and our audience watching at home is, what are the biggest surprises that we've gotten from this first year on Mars?
Yeah, and this is a great question for me, because I and many scientists who've thought about landing sites on Mars, we spent years poring over those orbiter images, trying to guess what's there and try to interpret what's there. And so going into this mission, I thought, I've thought of all the possibilities, and it's going to be one of those things that I've thought about, and that's how we're going to explain the rocks. But of course, Mars throws us surprises, and we certainly had that. One thing, thankfully, was not a surprise. And if we bring up slide 12, we thought from orbit that there was a lake and a delta, and you just saw that in the video. And when we got on the ground and we imaged towards the delta deposit, we saw this beautiful outcrop. And this is the kind of outcrop that you would bring a geology class on Earth to teach them about deltas. This is classic delta stratigraphy. And you see the layers in this image. The flat layers on top represent the upper part of the delta, going into those dipping beds as you get into the lake. And then as you get into those flat beds at the bottom, those are the layers that we look at for signs of preserved organics and possible signs of life concentrated there in the distant parts of these lake deposits. And so we were relieved that this was not a surprise. There is indeed a delta. We have confirmed it, and we have beautiful outcrops to show that we have this habitable surface environment preserved in Jezero. But there were still surprises in store. So if we bring up the next slide, slide 13, While we knew there was a lake and a delta here in Jezero, one thing we weren't expecting was signs of pretty active high energy flood deposits. And so that's what we're seeing here. This is an outcrop from the front of the delta, and that arrow there points to a big boulder, and that's an almost 1 meter wide boulder. And so in order to transport a boulder like that and the boulders in the surrounding outcrop, you need pretty high energy, energetic floods coming into the crater. And so we didn't know that that was happening here in Jezero. So we think we had this lake and this delta setting that transitioned over time into something much more energetic and perhaps catastrophic. And that might have been how water had its last gasp here in Jezero crater. If we bring up the next slide, while we had views of the delta when we landed at Octavia E. Butler Landing, seen here again in the orbiter image, we actually landed on the rocks of the Jezero crater floor. And we weren't sure what to expect of these rocks. There were different hypotheses thrown out by scientists. Are they igneous or volcanic rocks formed from magma or lava flows? Or were they sedimentary rocks? After all, we are in a sedimentary basin where we knew a lake was present. And so we had this question. And in this case, the orbiter data doesn't tell you the whole story. So we went into this thinking, you could probably split the team in half, those who thought it were going to be igneous and those who thought the rocks were going to be sedimentary. So the first couple of months of the mission, we were left scratching our heads about this question. The rocks weren't giving us many clues. They were dusty. Their natural surfaces were obscuring the kind of textures you would typically use to interpret the origin of the rocks. But by the time we got down to the location marked here at Rubion, which Jennifer talked about, the first place we took our sample, we had the opportunity to actually scrape through the natural surface of the rock to see what lied beneath. And so if we bring up the next slide, this is so this is our first abrasion. And Jennifer mentioned that these rocks have interacted, have been altered and weathered. And that's exactly what we saw here as well. You can see those holes, and those are holes in the rock, and not just caused by wind particle or sand particles blasting the rock. These are actually inside the rock, suggesting that water has moved through this rock and eaten away parts of that rock. But when we looked at this texture, this variation of light and dark minerals, this is pretty diagnostic and conclusive for an igneous rock. And we think it was formed by volcanic lava flows. And so the other neat thing about this, where we start to think about habitability and astrobiology potential, is that some of those light colored minerals you see there, those are salt minerals. And those only form by precipitating out of water moving through these rocks. So while we don't typically think of volcanic or igneous rocks as the prime place to look for signs of ancient life, at least here on Earth, given that water has moved through these rocks, there might have been habitable niches in this rock that are capable of supporting signs of ancient life. And so that's pretty exciting to find igneous rocks here. Those are great rocks to get age dates from and learn about processes in the interior of Mars, as well as to have this potential habitability aspect of these rocks as well. And so really exciting to have this kind of discovery. And to answer that question, volcanic or sedimentary, we answered that in the first year of the mission.
That's amazing to have those answers already. So taking those answers, because science is always about what's the next question? What can this teach us? Where can we go from here?
Yeah, so from a science and sampling perspective, and as a reminder, Perseverance is on the surface to collect samples for possible return to Earth. Jezero has been a slam dunk. We have, from the surface, even though we landed on the igneous rocks, we had views of the sedimentary rocks that we know are in the future of the rover and that we're heading to soon. But if we bring up slide 18, you'll see our current sample collection. And so this is the collection of samples that are currently inside the rover, getting ready in the future to potentially come back to Earth. And so we have a fantastic suite of rock samples that tell us again about the interior processes of a planet, the history of magma in the planet and perhaps erupting out on the surface as lava flows, and then a history of the interaction of these rocks with water that might have created the potential for habitable environments, as well as salt minerals that here on Earth we know are really good at preserving signs of ancient life here on Earth, and the same could be true for Mars. And so we've really hit it out of the park in this first year from a science perspective. We've got sedimentary rocks, we've got igneous rocks, and geysers really come through on the diversity and the interesting history of Mars as a planet.
That's wonderful. So, Nikki, I know I've got more questions, but what are they asking out there?
Yeah, so we've got a great question for Katie from Dan on Facebook, specifically about what the core samples are telling us. So, have any of the drilled core samples produced any evidence of biological material, or will we not know until they come back to Earth?
Yeah, that's a great question, and it's one that we think very carefully about. The bar is really high for scientists on Mars to make or scientists studying Mars to make an assessment of a potential biosignature. What I can say about some of these samples is that we have detected organic molecules in some of these samples, and organics are the building blocks of life as we know it. And so there's nothing that we have yet determined to be conclusively biological in the rocks that we've studied. But fortunately, with the potential for these rocks to come back to Earth, we can confirm that whether there are signs of ancient life here in these rocks. So I think we've very much collected a suite with the potential for that. But we haven't yet determined, based on our data collected on the surface, that any of the things that we found in these rocks or the organics we found in these rocks could only have been formed by life. We're not quite ready to say that, but fortunately we can answer that when these samples come back.